Hello, welcome to this video about the classics. Today I'm going to talk about the question 8. So I call L of f of t a function that for a variable p, so this depends on the variable p. It's a convention, so I forgot about it. We are going to call the integral between 0 minus and plus infinity of exponential minus pt times f of t times dt. Okay, so it's the Laplace transform of that function f of t. So we're going to calculate the Laplace transform of sine omega t, and then we are going to calculate another function that is not at all related but very similar. The four values of a, b, c. Well, C is actually not in that. Hold on, it's a mistake. How am I going to do that? A, B in R squared for because C needs to be positive because else it doesn't converge, and if it's 0, it doesn't converge. Yeah, if it's 0, it does converge. So 0 is included. Okay, so for all AB in R squared and for all C in R plus, so it can be minus LC. Well, oh no, because actually it does converge since it's not infinity here because it's not a limit, so it works for all values of C. It's just that you can't take an improper integral for this for values of C. So this actually works for definite integrals. So we call z of a, b, c the integral between a and b of exponential minus cx times sin x times dx. So we're going to do that right after. So first the Laplace transform. Let's scroll down, all the way down. Where is it? Not this. Okay, so we have this. Yeah, we're going to calculate the Laplace transform. So I just put the sin x. So we've got this integral. This time I'm splitting it with this this version of the formulas, trigonometric formulas. Okay, so we have this. So it's fine to split the integral. So I split this integral as being two integrals here. So we get this. We get 1 over 2i that comes from this part here. Exponential I omega t that is here minus. So minus is here. Exponential. Oh, there's a minus sign that is missing. Exponential minus pt times exponential minus omega t. So we get this expression here. So we just split the integral. So let's continue. I can just regroup this in a single exponential by the properties of exponential. Same here. Then I apply the integral. So when you take the antiderivative of exponential, you get the thing that is here inside, so 1 divided by what's here. So we get this. Oh, obviously, when you factorize by t, by t obviously, since it's a dt. So I factorize by t and I take what's the product of d in that exponential, and I do 1 divided by that thing that is here. So we have this times this thingy here, and the same thing here. So this is yeah. So I split again the exponential. So we have this that is equal. So this in plus infinity equals to 0 because this part we have the priority and it will converge greatly well normally to 0 even though this rotates in the complex plane, this will converge to 0, and in 0 minus this converges to 1, yeah, to 1, because this will have the priority, and in 0 this will just be 1. So we have the part in infinity that is 0 and the part in 0 minus that is here. So this equals to minus 1 obviously, and we have the same thing here. It's equals to minus 1 as well. So I can rewrite this with the minus 1 here and the minus 1 is equal to plus 1, so we get this. So I'm going to put that in a single fraction. So I multiply here by the conjugate and here by the conjugate as well, so I get this expression. Then I simplify, and then I see that we have p minus p, so it equals 0, and I omega plus I omega, so it equals to 2 I omega, so it's here. And then we have the 2i and the 2i here, so we can simplify it. So we get omega divided by pi squared plus omega squared. So this is very used in engineering. So as a side note, I'd like to hide that with the same method you can prove that the Laplace transform of cosine omega t is equal to p over p squared plus omega squared. It's just the same thing. Then let's talk about z. So let's do this. So we're going to use almost the same thing here than here, but we're going to use it differently because we're going to take the imaginary part. Where is it? It's there. Okay, so we have sine x that is equal to imaginary of exponential ix. So I can oops, since this is real only, I can factorize, I can put the imaginary before. We have an imaginary of this. So this integrals is equal to, with the same method as before, we factorize by c, so we get I minus c times x in the exponential here. So by the properties of integration of exponential, we get this expression, and same thing here. Oops, there's a minus, no, it's still the same integral, but I multiply by the conjugate that is I plus c, and we get this expression. So yeah, so we get this expression. Then I expand the exponential IB, because like here I can't like know what's the, well, technically I can, but I'm going to expand this as being a sum of cos b plus I sin b. So as we can see from earlier, sine is correctly the imaginary part of exponential ix. So exponential IB and exponential IA will be split back to this form. So we get this form. So we want to take the imaginary part of this. So at first, the constant part, this is only real, so it will not pose a problem. So we can factorize by this. So factorize by this. So the first thing, so we have an I here. So it means that to be imaginary, it must be strictly imaginary to be in the imaginary operator. So we want to see what's multiplied this that is real. So this is still a constant, so we can factorize it. So we've got cos b, that is a real, plus I sin b. So I plus I would be real, so we don't care, and I times b, but times cos b will be imaginary. So we write the constant that is here, times cos b. So it's imaginary. Then we do the same thing here. We have the same reasoning, constant, and then this part is real and this part is imaginary. So when you multiply by I, this becomes imaginary, this becomes real. So we get the same here. And then we have a constant c that is real. So we have this factorized by constant. We have this that is real. So real times real is real. So we don't care about it. And we have this real times this imaginary, so it's imaginary, so we put it here, and then we have the same thing here. So we have the result for all a, b, c in r to the third power. The a, b equals to this. And then that's it, we'll solve it. Thanks for watching, I hope you enjoyed it. And bye, thanks for watching. If you have any question, feel free to ask them in the comments. See ya!